looking through the assignments, I can see that an area where people had a little trouble is with problems like this. And I understand why, because the fractions are bad. And I made, this one's even, whoops, I gotta fix that a little bit, don't I? I need an X there. This is probably a little bit harder than the ones that show up on the assignment, but it's a good example to take a quick look at in class. How do we deal with this? Now let's ignore the ugly fractions for a second. Just think in terms of a process. What do I do if I'm trying to solve this linear system here? I mean, am I going to want to use substitution or linear combination / elimination? There's one of them definitely that I'm going to use here. One of them would not be a good fit. Whoops, sorry. Good. What do you think? Am I set up to substitute here? Do I have a variable isolated?
Well, yes.
Yeah, I do, don't I? In fact, I've got two. I've got y equal to some stuff here and y equal to some stuff here. This is already pre-packaged to substitute, isn't it? Right, I've already got my, and I can pick either one of those to be my substitution equation. It doesn't really matter. I'm just looking ahead a little bit here and knowing what I'm going to do. I'm going to substitute either all this stuff up here for the y in the bottom equation, right? Or I'm going to substitute all the x stuff in the bottom equation for the y in the top equation. I would rather have a larger number of x's on the left. Not that it's a big deal at all. You don't have to overthink this, but because I can kind of see that I want that to happen, I'm going to make this my substitution equation, right? Which just means that all of this stuff right here is going to go in for y. Okay, make sense? We good? All right. So if we do that, we've got the equation then 3/4 x plus 2/5 is on the left equals 1/3 x plus 1/4. That's terrible. That's a terrible looking equation. There's lots of fractions there, right? If we want to just follow the rules of algebra, think what we'd have to do. We'd have to subtract the 1/3 x from both sides. That's going to be bad. I got to subtract a bunch of fractions. I've got to add or subtract 2/5 from both sides. I've got to subtract different fractions again. It's looking ugly, isn't it? We're going to have lots of fractions to battle all the way through. Here is a great trick. This is the trick you want to use in situations like this. In situations like this, by that I mean situations where I've got a whole bunch of terms that are being added up on one or both sides of an equation that have fractions in them. In fact, sometimes, even if you've only got one fraction, you'd still rather not deal with it, and you can clear the fractions even then. We're going to take a really bad, really tough case where we've got 4 fractions to deal with. Now, the way we do this is we just have to figure out what is the least common multiple of all the denominators, meaning the least common denominator, of all the denominators on both sides. So what are the different denominators that I have in this case? 4, 3, 5, right? Okay, so what's the smallest number that those all divide into? You got to think about that for a second. That they all divide into, so it's going to be... They don't fit together really well, do they? And when numbers don't fit together well like this, and by that I mean, well, like 4 and 5 would be okay. I could pick 20, couldn't I? Right? But the 3 doesn't fit with that. If it was just the 3 and the 4, I could pick 12, but the 5 doesn't fit with that, right? 3 and 5 would be 15, but the 4 doesn't fit with that. So worst case scenario, just take the product of all 3, which is actually the answer this time, right? We know if I take the product of all 3 of those, for sure that's going to be a multiple of all 3. Maybe you can get a smaller number sometimes, but at the very least, that's the worst case scenario, right? So what's 4 times 5? 20 times 3? 60. So 60, that's it. That's the smallest number that they all divide into is 60. Okay? So then what we're going to do is we're just going to multiply that 60 through, distribute it through all the terms on both sides. And that sounds like extra work, but it's not. Trust me, it's really simple. Watch what happens when we do that. So if I distribute a 60 through, because that's the least common denominator, I want you to watch what happens here. Now there's even another trick folded into this that even makes it easier. If I just distribute the 60 straight through, because 60 is the same as 60 over 1, I get big ugly numbers. Like for example, 60 over 1 times 3/4, if I multiply straight across, would give me 180 over 4, agreed? That's a big number, a big fraction to reduce. I mean, we could probably do it, but it's still, that's kind of hard. Why not do this though? We can be really tricky about this. We picked this number 60. It's a special number because it's a number that we know 4 and 5 and 3 all divide evenly into, correct? Right? So why not kind of pre-simplify before we distribute? By that I mean, we could answer the question, 4 goes into 60 how many times? Now think about it. If I ever divide something by 4, what am I really doing? I'm just cutting it in half and then cutting that in half again, aren't I? Right? So what's half of 60? 30? Half of 30? 15, right? So 15, 60 divided by 4 gives me 15. Then all I have to do is multiply that 15 times the numerator. Much easier, right? Agreed? So when we're clearing fractions, that trick will always work. Always, first of all, just divide the greatest common denominator, or excuse me, least common denominator by the denominator of that individual fraction, right? So 60 divided by 4, 15, multiply it by the top, done with that term. So the first term then is just 15x. 60 divided by 5 is, what is that? 12. So 12 times 2 is 24. Okay. What about this side? 60 divided by 3? What's that? 60 divided by 3. 20, you hearing it? Okay, 20 times 1 is just 20. I need my x though, right? And 60 over 4 we already did, that's 15 times 1 is 15. That's easy, right? I'm sorry. Yeah, I didn't. Sorry, I meant to. Sorry, you're right. That was a good catch. I got to multiply the 15 by the 3, which gave me a 45, which I forgot to do, right? Whatever that number is, you multiply it by the numerator. So now we've got a really simple situation to deal with. No fractions, right? Our answer might be a fraction, but who cares? That's just going to be the final step is going to be maybe the answer ends up being a fraction. All the way through now, we don't have to battle those fractions. So solving this would be pretty simple from this point on. I would just maybe put all the x's over here, right? So what do I get if I push the x's to the left by subtracting 20x? What am I going to be left with? How many? 25. I want to push the constants the other way, right? So we'll subtract 24. Those go away. 15 plus negative 24. What is that? Negative 9? Is that right? Negative 9? Okay. So we get, kind of an ugly answer in the end. If I divide both sides by 25, I get 9, negative 9/25. It's kind of weird that it came out that. Like I said, yeah, I made this one up. So I wouldn't, the ones on the assignment, I would make them, they don't turn out so ugly. But there's my x answer. If I wanted to find my y answer, all I've got to do is plug that in. And yes, I am going to have to battle a few fractions when I figure out what y is, but it's not terrible. All I'm going to have to do if I plug this into, let's say, the top equation. So if I plug that in up here, whoops. If I plug that in up here, I'm going to get y equals 1/3 times, what was it, negative 9/25 plus 1/4. Yeah, I'm going to have some fractions to battle there, but it's a lot better than having to deal with it the whole way through, isn't it, right? So clear the fractions. Definitely highly advisable. Okay, the other thing that came up was real simple, but I'll save you a little time, was on stuff like this. This is just a sample of the first linear systems assignment. Look at these questions here. People made these a little harder than they needed to. If we we look at this, what kinds of questions are they expecting? We've got this linear system. They just want to know, do the two lines intersect? Are they parallel? Are they the same line? Okay. And if we know the answer to that one, I'm going to claim that we ought to know the second one is a freebie, right? So let's just look at the first one. A lot of people were going through and trying to solve this, to answer this question by solving the whole system. Is that necessary? No, it's not, is it? All we need to know here, if these lines are parallel or the same line or intersect, that can be determined by what? By what? I mean, when do two lines, how could we just by looking at the equation, and maybe I still have to do a little something with this one, but if I had them, let's say, in slope-intercept form, how could I tell just by glancing at them? We'd say math by inspection, by just looking at the equations. How could I tell if they intersect or not? Slopes. What about the slopes? If they're the same, would they intersect?
No.
No, they wouldn't, would they? Right? If they're the same, they're either parallel or the same line. If they're different slopes, automatically they have to intersect, right? Because the lines extend forever. So if they don't have exactly the same slope, they're going to cross, right? So what's our strategy here then? What's the slope of the top line? 1/3, isn't it? Right? We can see that because it's in slope-intercept form. The top one's already in the form y equals mx plus b. And so there's the slope, right? 1/3. We just need to know what the slope is of the bottom equation. And this is actually a really good algebra review topic for us. So how do I put that second equation into slope-intercept form so I can know what its slope is? I just isolate y. That's it, right? All I do is isolate y, and by isolating y, it's going to end up in slope-intercept form. So what are the two steps we have to go through to get that y by itself? I got to get rid of the 3x term. I got to push the 3x term to the other side by adding 3x and then dividing by 9. Okay, so let's go through that real quick. So negative 3x plus 9y equals negative 18. First we'll add 3x. That goes away, so I get 9y equals. Now these two terms don't add up because they're not like terms, so I'm just going to have to put them separately, right? Which one should I put first here, do you suppose? The x term or the negative 18? X, because I want it to look like that, don't I? So 3x minus 18, and here's the part that's maybe a little, maybe a little strange. Oh, I can't do that, can I? Whoops. Okay, so if I divide both sides through by 9, that looks a little weird. I've got the 9's cancel, but on this side I've got this common denominator. What can I do with that common denominator if I want to end up with an answer that looks like two separate terms? What can I do? I can simplify, but even before I do that, I can always take a common denominator and split it up among the separate fractions, right? So I could write this as 3 over 9, so 3/9, and I can pull the x out if I want to, that's fine, right? Minus 18 over 9. So what does 3/9 simplify to? So I got my 1/3 x minus 2. Okay, so now you tell me, are those lines parallel or not? Yeah, in fact, they're parallel. They're even the same line, aren't they? Right? So they don't cross, do they? So our answer would be they're the same line, and they're the same line. I didn't stick. Same line. There we go. And so if it's the same line, how many solutions? Infinite. Okay, what if, hypothetically, what if this had been, instead when I did the algebra, that had been a plus, come on, that had been a +2 instead of a -2. Then they're not the same line, but what? They're parallel. Good. And if the slopes had been different, if this had been something other than 1/3, I would have known that they intersect and there's one solution. I don't care what it is. They don't ask for the solution, right? Make sense? Okay, let's go. 332.